Now, I will define the tangent line. So, let us discuss tangent line to a space curve. Tangent line to a space curve. Tangent line to a plane curve was a simple thing. It is nothing but the limiting case of a chord. But when you have a space curve, there will be several lines passing through a fixed point of a curve. Infinitely many lines, none of them will be tangent except one. So, what is the speciality of that one line? That we will understand through the contact. You see, you can see, look at my finger. I can draw from this point many lines. You can see all of them are touching at a point, at the same point, but none of them is tangent except this. And this seems to be has a higher order contact than the other lines. This line has a lower order contact, whereas this is the highest, has the highest order of contact with the curve. So, how to get hold of this idea geometrically? So, suppose let us start with the curve C given in natural parameterization r equal to r s. This is a space curve regular. So, this is a regular space curve. When I say regular, I mean regular of certain order n, regular space curve with natural parameterization natural parameter is s, as you can see. And suppose there is a point P on it and its position vector is something r s 0. So, this is a point, let me write down little down. So, P is a point on C with position vector r s 0. So, this is a point, of course, it is regular point, it is a point on C. Now, consider a line passing through this point P. Consider a straight line passing through the point P. So, you have got two things, one is the point, one is the curve C, and the other is a line. So, this is some line which also passes through the point P. Let me call this line as L. Okay. Now, first of all, let us define how we will define the tangent line. So, with this background in mind, I am writing down the definition of a tangent line. A line L or a straight line L, a straight line L is said to be a tangent line or simply a tangent line to a curve C at a point. A straight line is said to be a tangent line to a curve C at a point P if what happens. Now, once again, what I will do, I will choose some point P over here, okay, and this distance from this, let me call it something q. suppose q is some neighboring point of P, and the arc distance from P to Q is h. Okay. And suppose and suppose the distance, perpendicular distance from Q to the line is d. Okay, I need not go through the point of contact, I can apply the theorem. Okay, so no need of doing all this, we will just apply the definition. Okay. So, this theorem will help us to discover the equation of the tangent. If it has a straight line L is said to be a tangent line to a curve C at a point P if it has a contact of order at least 1 or 1 order 1 with C at P. So, this is the defining part. If it has a contact of order 1 with C at the point P. Okay. So, this is how we understand by the tangent line. Any line passing through a common point will be called a tangent line if as a curve it has a contact of order 1 with the curve at a point P. Okay. All right. Now, we will work out the equation of the tangent line, equation of tangent line. You can interpret in terms of the contact, what do we mean by saying that it should have a contact of order 1? What are we demanding by imposing this condition? Okay, what kind of line we want, okay, so that it is a tangent line. This interpretation I am leaving for you. You see, whatever definition is given to you, you should interpret it geometrically in your mind what actually we are looking for. Okay. What kind of tangent line should be. All right. So, now let me work out the equation of the tangent line. So, I am assuming my curve represented by this equation, and suppose let me write down here. So, our curve C is r equal to r s, and suppose the point P has coordinate r is 0, and suppose the line is also a curve, it has some parametric representation. So, line as a space curve can be represented by an equation r equal to, it is passing through the point P. So, it must be r is 0, it has certain parameter sigma into it is parallel to some vector A. Okay, this is how you write down the equation of a straight line in space. Let me recall it for you. Suppose you are given a line which passes through a point P whose position vector is something say lambda, and suppose the position vector of an arbitrary point is capital R, and suppose this line is parallel to certain vector A. If you are given two things about the line, the point from which it passes and the vector to which it is parallel, you can write down its equation. So, its equation, suppose the distance from this point P to this point Q, Q is arbitrary point, must be something say sigma. Okay. So, its r must be equal to, you can look at the vector r equal to lambda plus sigma times A. Okay. This is how the equation of a straight line looks in 3-dimensional space. So, in our case the point P is r as 0, this is the distance sigma. So, since I will vary my point Q, this sigma will vary, which can be treated as the parameter, arc length parameter, and A is a vector, unit vector, which to which this line is parallel. So, here A is a unit vector, parallel to the line, and sigma is the parameter of the straight line, arc length parameter, of course, parameter of the natural parameter of the line. Okay, so you have got two equations. This is number 1 and this is number 2. So, 1 and 2 are two curves with me, and what I am given is that they have a contact of order 1 with each other. So, if they have a contact of order 1 with each other, now apply the previous theorem. So, since L and C have a contact of order 1, by the last theorem, we have now since this is a function of sigma, because parameter is sigma. So, right side is sigma. So, they must coincide at the point P. So, we have number 1, r as 0 must be same as r 0. The value of sigma at the point P must be 0, because you are computing along the line from P to here, this distance is sigma. So, here it must be 0. Okay. This is obviously true. Okay. And number 2, their derivative must coincide. So, the derivative of the first at S 0, r dash as 0 should be same as r dash sigma r dash 0. So, we need to compute r dash 0, which I can do from here. When I will take capital R dash, I mean derivative of r with respect to sigma. So, this will be treated as constant. So, the derivative of the first term in the right side will be 0, and this is also a constant vector, it will only be. So, r dash sigma by 2, r dash sigma is equal to 0 plus A. Okay. And this must be, according to the last theorem, this must be same as r dash as 0. Okay. So, this A which was unknown to me becomes known from this condition. So, the equation of the tangent reduces to the following. Hence, equation 2 becomes, hence equation number 2, that is equation of the tangent, equation of tangent at P reduces to becomes r equal to r is 0 plus sigma times r dash as 0. So, this becomes the equation of a tangent line in the vector form. This is the, you can say it is a vector equation of the tangent line. All right. You can convert into Cartesian form also, and into generalized parameter. All these things can be done at this point. You see, suppose we are given the equations of the curve and the line in Cartesian coordinates. So, we can rewrite this equation in terms of Cartesian coordinates. So, we can express the above equation in Cartesian coordinates as follows. Okay. The vector r is a vector in R3, I can assume, and it is an arbitrary vector over the line. So, I can take its component as capital X, capital Y, capital Z. So, these are the x, y, z components of R. Put a bar over here, and R as 0 is a point. R as 0 is a point on the curve. Let me denote these points components by x 0 or x s 0, whatever you call it. Okay, x s 0, y s 0, z s 0. Okay. This is the vector R s 0 plus some sigma times this vector r dash as 0 r dash as 0. Once r as 0 is this, r dash as 0 must be x dash as 0, y dash as 0, z dash as 0. Okay. So, or you can more simply okay. So, this becomes, in short, I will call it x 0, x 0 plus sigma times x dash 0, y 0 plus sigma times y dash 0, z 0 plus sigma times z dash 0, and this vector and this vector are same. So, you get from here that x equal to x 0 plus sigma times x dash 0, y, if the two vectors are equal, their components are equal. The y component is equal to y component, this much, and the z equal to z 0 plus sigma times z dash 0. And from the first relation, I will be getting x minus x 0 upon x 0 dash equal to sigma. From the second relation, you will be getting y minus y 0 upon y 0 dash also equal to sigma, and from the last relation, z minus z 0 upon z 0 dash equal to sigma. If you write all the three relations together, you can say that x minus x 0 upon x 0 dash equal to y minus y 0 upon y 0 dash equal to z minus z 0 upon z 0 dash. All of them are equal to sigma. Now, this x 0 dash, if you look at this equation, this is the Cartesian form of the box equation. Okay. This is in the vector form, this is in the Cartesian form, both of them represent the same tangent line. So, this is the equation of a line, the denominator represent the what direction cosines. Okay. If the right side is is the distance between the two, then they will be the direction cosine. All right. This is the equation of a line. Yes, yes. Okay. So, this is the equation of the tangent line in Cartesian form. This is the equation of tangent line in Cartesian form. Here x 0 dash, y 0 dash and z 0 dash are the direction cosines of the tangent line. This fact I can write down here. Here x 0 dash, y 0 dash, z 0 dash are the direction cosines, are the direction DCs of the tangent line. Okay. Okay, how much time is? Okay, let me take up one more example, so that so you see we have a non-trivial space curve which we have been dealing with. In fact, there are many other curves also, but we most often talk about the helix. So, let us find out the equation of the tangent line to a helix. So, as an example, consider a circular helix. Consider a circular helix. Its equation you know is x equal to a cosine theta, y equal to a sin theta and z equal to b theta. I want to find out the equation of tangent line at theta equal to something theta naught. Okay. So, according to, if you want, since the coordinate x, y, z are given to me, I will write down the Cartesian equation. So, equation, Cartesian equation of the tangent line, Cartesian equation of the tangent line to the curve at theta equal to theta naught is given by so x minus a cos theta naught, x minus x naught, okay, upon the derivative of x. The derivative of x will be minus a sin theta. So, that is minus a sin theta naught equal to y minus a sin theta upon y dash 0. Y dash will be a cosine theta. So, a cosine theta at theta equal to theta naught equal to z minus z 0. Z 0 is b theta naught upon what? Derivative of this will be just b. Okay. So, this is the equation. Now, in particular you may be asked to find out the tangent line at theta equal to pi by 4 or pi by 3 or anything. You just write down their values, that will give you the equation of the tangent line. And if I ask you what will be the unit tangent T, the unit tangent vector to the curve at say theta naught, it is r dot upon mod r dot. So, what will be r dot? R dot will be, it is r dot upon mod r dot. This is the unit tangent. Most of the time we will be denoting the unit tangent by the symbol t. So, that will be r dot, if you recollect, it is this x dot. X dot means minus a sin theta. You are computing at a point theta naught. So, okay, theta naught, and then a sin a cos theta, and here it will be just b, and its modulus you can see a square sin square theta plus a square cos square theta plus b square means 1 upon a square plus b square. This is the unit tangent vector, whereas this is the equation of the entire tangent line. So, there are many other examples given in the lecture notes. You can consider those tangent examples. They are simple, or you can take up some other example also. So, I stop at this point and we will continue in our next lecture.